Swayam Prabha. Digital India. Educated India.
Then comes the channel routing. Channel routing is, we don't have anything. Oh, I forgot one thing. See, when the reservoir has an uncontrolled outflow means I am not stopping any surplus through a gate, right? Whatever the flood water comes, it goes out naturally without any control. Then this outflow hydrograph always crosses at point of inflection in the recession limb of inflow hydrograph. Please remember that. Right? Whereas in channel routing, I need to find out or I need to solve the dynamic equation of continuity and momentum equation of Saint Venance because I don't have storage there. Okay? So I need to solve the continuity equation and energy equation to find out the flow parameters, discharge, right, V, and then Y, depth of flow at different sections X, and the discharge. So these three parameters we need to keep in mind or estimate while doing this hydraulic routing. So there is another method, right? I said channel routing is somewhat complicated or difficult to arrive than the reservoir routing because you can safely dispose the flood from the reservoir than a river which is continuously flowing because of lot of other constraints. So that is why people say that channel routing differs from reservoir routing in that storage in a river reach L depends upon more than just outflow. Okay, that is no storage in channel routing. The peak flow of auto hydrograph from a reach is usually attenuated and delayed compared with that of inflow hydrograph. Whereas in channel routing, I have two sections at a distance of L meters. Then the inflow at one place and outflow at another place. Then I will have two inflow and outflow hydrographs. Okay. Then the third is, since storage in a river reach is a function of whether stages rises or falling. Storage in this case is function of both outflow and inflow, not just because of inflow alone. See, the increase in reservoir water level is function of inflow. Okay, but in a river reach, suppose if there is huge amount of inflow, water level goes on increasing. Similarly, when there is huge amount of outflow, it goes down. When inflow is zero, water level goes down. It is fluctuating. So it is function of both inflow and outflow. Finally, the reservoir routing is generally easier to perform than river routing because storage discharge relationships of pipes, weirs, right, different types are all independent of flood flow. For example, you estimated depth of water over the weir and discharge. It is irrespective of whether the storage has been built up due to flood or not. Okay, so such things will be easier. For example, this is a figure taken by our people in some book, right? You see here, level pool means reservoir routing. So I have a space to store, and the outflow Q is not function of inflow; it is function of depth of water over the weir. Okay, if it is orifice, the discharge is function of height of water. Similarly for weirs, so inflow and outflow will look like this and it crosses. If it is a channel routing, right, in this case my outflow is less than inflow, then my water level looks like this. If my inflow is equal to outflow, my water level looks like this. My inflow is less and outflow is more, then the water level looks like this. So finally the reservoir channel routing also like this, right? But when my river is very large and it can accommodate certain quantity of flood, that means certain storage, then we can still employ the hydrologic equation for channels, and that is called as hydrologic channel routing. Right? In reservoir routing, storage is unique function of outflow discharge, and storage is function of both outflow and inflow in channel. Therefore, different routing methods are needed. Okay, so the river flow during floods belongs to the category of gradually varied unsteady flow in a river reach. This is very important. Gradually varied unsteady flow. But water is not only parallel to the channel bottom, but also varies with time. Right? Let us see this classical drawing to explain how the wave moves between two sections. Let us consider section 1 at downstream side and upstream side at a distance of L. Now you see initially the water level moves like a rectangle, right? That is prism. But as the flood water starts moving up, it slowly increases the height and then makes a peak depth and then becomes a constant depth. So then what happens? There are two types of storage. One is a rectangular shaped storage, that is called as prism storage, and then irregular shape, that is called as wedge storage. There are two types of wedge storage, positive and negative. Positive is building up, negative is depletion. Now this prism storage that exists if uniform flow occurred at the downstream side. So the prism storage, rectangular storage, is function of outflow, whereas wedge is due to flood. Flood comes from inflow. So therefore wedge storage is function of inflow and the prism storage is function of outflow, because this prism storage happens due to uniform flow because it is layer by layer, whereas wedge storage is a gradually varied flow which is happening due to the inflow. So then what is the total storage? Total storage is directly proportional to in storage due to inflow and storage due to outflow. But how much of inflow is stored and how much of outflow is stored? Let us consider a coefficient x. So the x quantity of I and the remaining 1 minus x quantity of discharge. That's a non-linear relationship M. So storage is directly proportional to function of inflow and outflow, the total storage. So it is expressed as, to remove the, to make a equality, S is equal to K and x to the power of Im plus 1 minus x to the, into Q to the power of M. This is the general hydrologic channel routing equation. That means I don't use Saint Venant's equation or momentum equation and energy equation to estimate the depth and the velocity. I am just simply estimating the volume estimated from the inflow and the outflow, and this is highly non-linear, right, because I to the power of m. K and x are called as coefficients and m is a constant. Then what happened? People started using this hydrologic channel routing equation, general equation, for a particular stretch. It was first tested with a river called Muskingum River, and that has become a Muskingum equation of channel routing. There are certain assumptions they made in this Muskingum channel routing. The Muskingum is a river in Ohio state. It's a tributary of Ohio River. The length of this stream considered is 179 kilometers. The basin area is around 20,850 kilometers. Okay. So what assumptions they made? The first assumption they made is the relationship between storage and inflow and outflow is linear. That means m is equal to 1. Okay, then straight away s equal to k into xi plus 1 minus x cube. And then they assumed that this weighting factor x and k, storage constant, is not function of flood. It is function of channel characteristics. Whether the flow is due to normal flow or flood discharge, this K and X can be estimated prior to a flood and keep that as a ready reference, right? So if let us assume that the inflow is 0, that means flood water is 0, that means X is also 0, then storage is mainly due to Q. When there is only outflow, inflow is 0. If only there is inflow and outflow is 0, then my storage is equal to K into I. Okay. So the X value varies between 0 to 0.5 and K is the storage time constant, also called as travel time of the flood wave through the channel reach. How much time is taken by the water to move from section 1 to 2? Saying that this K and X are called as Muskingum parameters. Right? Let us see how they have estimated this Muskingum parameters. Like a reservoir routing, channel routing can also draw the inflow and outflow hydrograph. Assume that this is the inflow hydrograph and this is the outflow hydrograph. Consider the small time period delta T. Okay. Now for this delta T, initially there is a build-up and then this is a outflow, depletion. So then what happened, for every delta T, I am estimating what is the cumulative storage. So initially what happened, when I plot time versus this accumulated storage, as the time increases in the inflow outflow, there is a build up in storage. Right? So my accumulated storage is increasing. Once it reaches the peak value, with further increase in time, the outflow is more than the inflow, so there is a reduction in volume. So my cumulative becomes smaller and smaller and reaches the 0 value. So this itself, the accumulated storage itself will look like an hydrograph, and this is called as summation of incremental storage versus time. And this is the water balance equation, hydrologic equation used to estimate this curve. If I want the final storage, it is accumulation of each and every storage. Now, how do you estimate this K and X? First assume you have a flow in the river, but not the flood flow, some other flow. Then first you assume a value of X and estimate this quantity xi plus 1 minus x into q for various time intervals. Okay, draw a graph between the storage and this estimated storage. If the assumed x is correct, then we will get a linear line, else a loop. Because see, when I estimate the storage, accumulated storage due to Muskingum, initially it is building up, then it has to come in the same depletion rate, right? Then only it will reach 0, otherwise it will make a loop, then the value of x is wrong. So you have to go on estimating this value of x by trial and error. That was the first method. Nowadays people are using genetic algorithms, subcomputing techniques to estimate this value of Muskingum parameters. Right now, either I estimate this storage xi using this Muskingum storage or from my mass balance equation, right? I minus q is equal to delta s. Storage remains the same. That means it has to be a straight line. Then that slope of the straight line will become the value of k in Muskingum equation. Let us see how to estimate this. See, the following inflow outflow hydrographs were observed in a river reach. Okay, estimate the value of k and x, which can be applicable for this reach to use in the Muskingum equation. This is a non-flood equation, non-flood hydrograph. So this is the time, this is the inflow, this is the outflow. So first what we have to do is, I know this is the inflow, right? This is the outflow. Now what is change in storage? I minus q, right? I minus q at a given time period. average I minus q, right? Or you can re-estimate also I1 plus I2 minus q1 plus q2 by 2, right? So the average change in storage is 7 meter cube per second, multiplying it with the delta t 6 hours. So this is the storage, right? That means this curve I am building up, I am estimating this delta s from start to the end. Initially it is positive, then it goes on negative. Now I am finding the cumulative, right? So I started estimating the storage build up for delta t, and then storage depleted due to delta t. Cumulative, right? It go on adding. This is the storage hydrogram. Now what happens? This is storage estimated using my mass balance equation, right? This column. Now I have to estimate using Mushkingham column, which is equal to xi plus 1 minus xq into k. For that I assume a x value. Now I assume x equal to 0.35. So multiply each inflow with 0.35 and outflow with 1 minus 0.35. So total it is 5. So 20 multiplied with 0.35 and 6 multiplied with 1 minus 0.35. So you are having this graph. Now I am plotting the relationship between this accumulated storage estimated using mass balance and accumulated storage due to Mushkingham, right? Storage from continuity equation 1 xi plus. Now what happened? It is slowly increasing, but while returning after peak flow, it is making a loop. That means my x value is wrong. So what I do? I change the x as 0.3 and re-estimated. That means 5 into 0.3 plus 0.7 into 5, that is 5, or 20 into 0.3 plus 6 into 0.7. So you go on estimating like this, but this remains same mass balance equation, right? Now you plot it, still there is a loop, so you go on increasing. So when x equal to 0.2, it is almost a straight line. The slope of this equation, here I have used it in y-axis, so the inverse of the slope of this equation will give me the value of k, right? So for a given channel reach, k and x are assumed to be constant. So this will not change with respect to time, but changes when the shape and channel bed characteristics are changed. So for a given channel reach, by selecting the routing interval delta t in the Mushkingham equation, S2 minus S1, right? I2 plus I1 by 2 delta t. So this is my mass balance equation where delta t is involved. But in continuity equation, I know the storage at starting of the time and the storage at end of the time. So then the difference between these two storages is the storage due to Muskingum method. So S2 minus S1 by Muskingum method, K into I2 minus I1 plus 1 minus X into Q2 minus Q1. Whether I estimate the difference in storage using mass balance or using Muskingum, both should be equal. That means equation 12 right hand side is equal to values of equation in right hand side of equation 13. So in this, right, I estimate in this 2 equations, the unknown is Q2, right? All other things are known. Bring the unknown to one side, right? So I will get Q2 is C1 I1 plus C2 I2 plus C3 Q1, where C1 is function of K, X and delta T. C2 is also function of K, X and delta T. C3 is also function of K, X, delta T. So I request each and everyone to derive this and find whether you are getting these values. Right? I will upload the PowerPoint to the Moodle today. The beauty of this coefficient is this: the algebraic sum of all these 3 coefficients must be equal to 1. Then we can say that the estimated coefficients are correct. If it is not equal to 1, then the estimation is wrong. Okay, so you have to re-estimate. Then these three coefficients C1, C2 and C3 is called as Muskingum coefficients. Please remember K and X are called as Muskingum parameters, which is function of channel characteristics, and C1, C2, C3 are Muskingum coefficients, which is function of channel characteristics and delta T. Okay, so this values are needed if I want to know the flood routing through Muskingum channel routing. Okay, so then I know what is the discharge at different time step, which is function of inflow at delta T starting, then inflow at end of delta T and starting discharge and these coefficients. Okay, and this equation is known as Muskingum flood routing equation. Okay, so I have given an example. Route the following hydrograph through a river reach. K is given. You see the unit of K is hour and X is a coefficient. Okay, and the only data required is the hydrograph, inflow hydrograph and discharge at end of at starting of the flood. Right. Now this is the procedure. Knowing the value of K and X, select an appropriate value of delta T, calculate C1, C2, C3, then start the initial conditions and then calculate Q2. Okay. So I just worked out also for given K, C1 is 0.4, C2 is 0.048, C3. So when I add this, it should be 1. Okay. Here I adopted 6 hours as the delta T because my inflow is given at every 6 hours. Then I do it in a tabular form, right? This is starting 0. So 4.29 I1, this is 10 into 4, this is I1 for 0 to 6. I2 is 20 at 6. Then Q1 is 10 into 0.523, add it, you will get discharge at time step 2. Now 20 will become I1 for 12th hour and this 50 will become I2 and this 10.48 will become I1. Find out, add all these things. So like that you go on substitution. Right? Here also you can see that how the inflow and outflow are varying. There is a large difference between peak flow. Here the peak flow 60 happened at 18th hour. Here the peak flow is 49 meter cube per second happened at 30th hour. That's a large gap, lag in the peak flow. Okay. So all these measures are mainly to reduce the flood damages. Right. There are two great methods in flood control. One is structural method, another one is non-structural method. Okay. The structural method is storage and detention reservoirs. Right? You construct or increase the capacity of the reservoir or construct one more reservoir called as flood storage reservoirs. Then levees, that means when I estimated the Saint Venant's equation, I found that there are certain locations where the depth of water is more. Then what happens? You construct an embankment so that the flood water is well within the river. But outside that flood embankment, the water level, the land level may be much lower than the water level. For example, if you travel in Godavari, there are flood levees from Rajmundry to Bhadrachalam, right? From Bhadrachalam to Rajmundry, you can see an earthen dam like structure on both banks of the river Godavari. They are example of flood levees. It's nothing but earthen bund which retains the flood water within the river. Or you do the channel improvement, that means you reduce the resistance of earth, make your discharge to flow at faster rate. Or floodways, or that means if this channel is unable to take, make a new additional channel, right, parallel to that or at a far off distance, so that the flood water will move in that additional channel. Or you do soil conservation service at catchment area. If these structural methods are not helpful, you announce a particular zone as the floodplain. Okay, so these are all the methods to flood control. With that, I'm winding up this flood forecasting also. Next class we will start with water resources engineering.